Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the EMFT. Today in this video, we are going to talk in detail about the Biot-Savart's law. In the previous video, we already introduced the concept of the magnetic flux density, how we can derive the magnetic flux density from the Ampere's law of force, that also we had already seen. So now it's the time to define a very fundamental law of magnetostatics, that is the Biot-Savart's law. I hope you remember how I defined the magnetic flux density. That is the utmost thing that is desirable in this video. So if you have still not watched the previous video where I talked about the magnetic flux density, it is highly recommended that you go back, watch it first and then come to this video. So now let's start our discussion on the Biot-Savart law, which is the fundamental law of magnetostatics, right? So it is going to give me what is the magnetic flux density arising at a specified point P from a given current distribution. I know if I have a single current distribution, it is going to generate some magnetic field, right, surrounding to it. So this magnetic field we can compute with the help of the Biot-Savart's law. Right, so the contribution of the magnetic field at the point P from a differential current element IDL is given by the formula dBr is equal to mu naught I. So this is the small magnetic field that we have, dBr. So it will be equal to mu naught I upon 4 pi dl dash cross r upon r cube, right? So this dl dash is a small element that we have taken cross r vector upon r cube. So this is how we can define the small magnetic field arising out of a current carrying element dl dash, right? So here you can see we have the idl dash vector and here this is my point P. So this vector is the capital R vector from the IDL to the point P. The small r is the vector over this point from the point O, let's suppose, and here from the point O to the element IDL dash we have R dash vector, right? So here you can see this is the distribution that we have and we have the small magnetic field arising out of this distribution. Now if I have the entire circuit, as of now we have computed the magnetic field, which is a small magnetic field due to the small element only. Now due to the entire circuit, if I need to compute the magnetic field, so I will be taking into this consideration of the integration. So now I told you that the circuit will be a closed loop circuit. So here I will be taking the contour integration. So the total magnetic field BR will be equal to contour integration mu naught I upon 4 pi dl dash cross r upon r cube. So this is how I can compute the magnetic field for the given current element. Now for the total current I am finding out this magnetic field. Now when I have the surface distribution of the current is distributed over the surface. This is how we had found out the magnetic flux due to the line distribution of the current. Now current is distributed on the surface, so BR will be equal to integration over the surface mu naught ISR cross r upon 4 pi r cube ds. So now here we will be taking the surface integration, otherwise all of the parameters would be same and the current here I would be taking the surface current, right? Otherwise the formula is same. Similarly, if I have the volume distribution of the current, so the Biot-Savart law will be like integration over the volume mu naught JR dash. So this is the volume distribution of the current, right, cross R vector upon 4 pi r cube dV. So now what is this surface distribution of current? What is this line distribution of current? And for the line distribution of the current I had taken I. For the surface distribution I have taken JS. For the volume distribution I have taken JR. So what is this surface distribution, line distribution and the volume distribution of the current? So let's understand this, because for finding out the magnetic field we are using these things. So first of all, I am going to relate it with the charge. So how the current is related? Current is related directly to the charge. So line charge will be related as the line current density, right? Surface charge will be related as the surface current density. Volume charge will be related as the volume current density, right? We all know what was the line charge per unit length. So here the line current density is different from the line charge. So it is occurring for the infinitesimally thin filamentary bodies. Whenever I have a current element, so let's suppose this is my current element, but it is having a very thick boundary, right? So it is having some radius, but if I consider that it is not having any kind of radius, it is very thin, it is infinitesimally thin, the thinnest thing you have. If you are you consider your hair, it is a very thin body. So now here, if you consider any conductor which is comparable to your hair, so that would be infinitesimally thin, and for that I will be finding out the line current density. So it is considering the wire of negligible diameter, and the line current density will be directly equal to the current. So it is directly equal to the current, so JL can be represented directly as I. So in the first formula I have represented mu naught I, right? So now coming to the surface current density. Surface current density is occurring for the body which is perfectly conducting, right? So now here the surface current density is given as current per unit width. So here, if let's suppose this is a body which is perfectly conducting, it is having some radius, some width. So if I am considering this width to be d over here, so surface current density would be the current per unit width, right? So Js is equal to I upon d. So this is the surface current density that I have, right? After that we have the volume current density, which is the most common current density we use. Whenever I ask you what is the current density, you say current per unit area. Now this is not the current density, this is the volume current density actually, and it is used most commonly. JB is equal to current per unit area. J is equal to I upon A. So this is how I can have the different types of current distribution, and here in the volume distribution I will be using the volume current density. Here in the surface distribution I will be using the surface current density. So I hope you understood the Biot-Savart law, how I can represent the magnetic field using the Biot-Savart law in the volume charge, in the surface charge, and the linear charge distribution. So if you have any doubt, you can put the doubt in the comment, and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.